Hello, so today in class, we're going to begin our journey into what are known as sequences. And sequences, as we'll see, are basically infinite lists of numbers. And the notation we use for sequences is basically coming from set theory and set notation, where say we have a series of a sub n from say n equals 1 to infinity. And just to tell us, we have our index, where n is literally marching from n equals 1, n equals 2, n equals 3, all the way towards infinity. But we also have this other aspect, which is sort of our generating function of how we get every element in that infinite list. So for us right now, just going with these indices from n equals 1 to infinity, our elements of the list would be something like A1, A2, A3, A4, and again, we would march all the way towards infinity. So we're going to try and get comfortable using this set notation. Some of the other questions we're going to ask in class is whether a sequence converges or diverges, and we'll discuss what that means. In a nutshell, what that sort of looks like is we ask the question of way, way far down that sequence or way, way far down that infinite list, do all of the elements begin looking identically the same? And that brings us towards what is called a convergent sequence. As we'll see, we're going to use limits extensively to help us answer that question. We'll also introduce some other ideas such as monotonicity, or is a sequence monotonic? And for us, what this means in terms of monotonic would be if we took each of these A1, A2, A3, A4, and so on, and we plotted them. So just say n equals 1, n equals 2, n equals 3, n equals 4. And on the vertical axis, this would be that value of that specific n value a sub n. It is monotonic if we see that the sequence is either always increasing, so the values are either going up or staying the same, or it's monotonic in the other case if all the values are decreasing. So monotonicity is basically a definition for us where the values of our list might be always increasing, they might be always decreasing, but if either of those two cases are true, in that case, our sequence would be called monotonic. The other definition we'll introduce is what is called bounded. And again, for boundedness, we go back to every element of that sequence or every item in our list. And we start asking the question, hey, is there a lowest value that none of those values gets below? Hey, is there a highest value that none of those values gets beyond? And if so, then we get to call our sequence bounded. So this would be like saying, if each of our values in our sequence, they don't have to be monotonic for bounded, but what if every value was really struck or stuck between two specific bounds, and we just had values that maybe went up and then went down, but for all time, these values are just going to be stuck between those upper bound and that lower bound, or that top line and that bottom line. If that's the case, we call this sequence bounded. And again, we'll formalize all these definitions as class comes, but I just want to introduce you to some of these ideas of monotonicity and boundedness before we get there. And the other special thing is when we have a sequence that is both bounded and monotonic, we're going to be able to say through a theorem that in that case, the sequence must converge. So that's basically what's on tap for talking about sequences and our introduction towards them.